I'll begin.
Yeah.
Okay, fine. So let's start with forces. I think we discovered or we discussed about forces in yesterday's class.
Yeah.
I'll just talk about force again. Yeah. So what is force according to you?
A force is a push or a pull or a phenomena which has an effect on any body, which makes it move or stop or change direction, change speed, or rotate.
Change shape also?
Yes, change shape also.
Yes, correct. In fact, that's what we spoke about, right? A spring. A spring does the exact same thing. Correct?
Yes.
Yeah. Okay, fine. So these are all the effects that force has on a body. That's correct. So let's talk about force one by one. In fact, let's talk about force through Newton's laws. Okay. So can you state Newton's first law to me? However you remember it. That's perfectly fine.
Okay, so the first law of motion is that any object moving in a straight line or in a state of rest will continue to do so until acted upon by a resultant force.
By an external force. Correct.
Yeah.
Correct. Yes. One small change. It doesn't have to be a straight line. A body in motion continues to be or continues to stay in motion, and a body in a state of or at a state of rest continues to be in a state of rest unless acted upon by an external force. Correct?
Oh.
So basically, it talks about the concept of inertia.
Okay.
Can you define what inertia is? Here it says that the more the mass, the more the inertia of a body. But can you give me like a solid definition as to what inertia means for a body in physics?
Maybe
In your own words. I don't need a textbook definition.
inertia. So
Hmm.
I don't know how to explain it.
Think of it this way. Inertia is basically what is explored in Newton's first law. It's the tendency of a body to either be in a state of motion or be in a state of rest. That's what inertia is. Okay?
Okay.
It's the tendency of a body to be in a state of motion or be in a state of rest. What I'm trying to tell you is the ability of a body to stay at rest unless a force pushes it or compels it to move, or the ability of a body to continue or keep on moving until a force pressures it or a force asks it to stop. That is called inertia.
Okay.
Yeah. There are two ways you measure inertia from Newton's first law. One is called, you've learned these concepts. One is called momentum.
Okay.
Which is denoted by what? What is the symbol for momentum?
P.
Momentum P equals
MV minus
mv.
NV.
Exactly. Momentum is just product of mass into velocity. That's all it is in simple terms. Got it? Okay. And do you know the other quantity you use to measure inertia?
Impulse.
Exactly. What is impulse by definition?
Impulse is the rate of change in momentum.
Impulse is just change in momentum, not rate. Rate of change of momentum is actually force, which we will talk about in a while. No problem. If a body's, let's say initial velocity is u, final velocity is v, then the impulse is just mv minus m. Am I correct?
Yes.
There is also another formula, which I will write in a while.
Force into change in time.
Exactly. Correct. Force into change in time. I'll explain how that formula came about. Force times time. Next, let's go to second law. Second law is basically the personification of the formula F equals ma. Correct?
Yes. It's yeah.
That's all it is. F equals ma. So I'll teach you how it is derived. You don't need to know. It is derived like how all formulae are derived. I invented a quantity called force. I figured out that this quantity of mine, force, by definition, depends on the mass of the body. It depends on its acceleration. So I combined to write the equation. F is equal to constant k into mass into acceleration. Because I defined this quantity and its formula, I'll define the constant k also to be of value 1, giving me the equation F equals ma. Simple?
Yeah.
That's it. How I want is how I derived. There's no logic. There's no hard math involved in this. Clear?
Yes.
Now, let's take the body for example. Let's take a body of mass m traveling with some initial velocity u. Let's say after the application of some value of force F, its velocity changed from u to v, but the mass is same, m. So here, force is causing a change in momentum. Is that correct?
Yes.
And if you remember your equations of motion, what is the formula for acceleration? A equals?
V minus U by T.
So substituting this A equals V minus U by T here, I get F equals mv minus mu by T. Correct. Or force can also be written as change in momentum divided by change in time. But since change in momentum is impulse, I can also write force as impulse divided by change in time. This helps me rewrite the formula. Impulse equals force into time. Got it? Any doubt on this?
No.
Anything you want me to explain again from Newton's first and second law?
No.
So these are my interpretations. Make sense?
Yes.
Yes. Okay. Fine. Do you need a minute to copy anything?
No.
No. Okay. So this is your formula for resultant force. F equals m. Got it?
Yeah.
Okay. So before we go to friction, let's talk about Newton's third law, which gives you the collision ka equations. Newton's third law is very famous. It's
Yes.
I think you'll know this.
Every action has an opposite and equal reaction.
Equal and opposite reaction. Can you give me an example?
Okay, so for example, I have to dive in a pool. So the force I'm going to apply to the diving platform, with that force, the diving, okay, not maybe a diving platform because it's fixed to a point, but if I'm moving from a place from a surface which can move itself, so with that force, it will move backwards. I don't know how to put it in words.
Any physical example? You pushing the pedal of a cycle?
Yes, but yes.
Yeah. The part I'm talking about is where your legs start to hurt. When you, cycling is an exercise, right? There's a reason why it's an exercise.
Yes.
The reason it is an exercise is because when you push the pedals on the bicycle, the pedal applies an equal and opposite force on your legs. This strain causes your muscles to exercise. Correct? I can talk about an even simpler example. The act of you sitting on your chair right now. So right now you're sitting on your chair, but can you sit for long?
No.
No, you can, but your back will start to hurt.
Yes.
Why does your back start to hurt? Because you're applying your weight downwards now. Why does your back hurt?
Because I don't know.
Newton's third law. Use that to explain why does your back hurt.
The chair is exerting some sort of force.
Correct. So whenever you're applying your weight on the chair is applying an equal and opposite force on your back.
Oh.
This force applied by the chair on your back is the reaction force. You applying your weight on the chair is the action force. So every action has an equal and opposite reaction. Correct?
Yes.
Clear? Another simple example. Let's say I try to punch a wall. Unless I'm the Hulk, I'm not able to break the wall, correct?
Yes.
And when I punch a wall, what happens? My hands hurt, my knuckles hurt. The reason is same thing. Every action has an equal and opposite reaction, correct?
Yes.
I have a question though. Seems stupid. Why does it not hurt when I punch a pillow though? You're telling me there's no Newton's law is not obeyed there?
No, it will be obeyed, but I think because the pillow is not a rigid surface, so it's going to and
Absorb a part of the force.
changes shape. It changes its shape.
Exactly. We've discussed a while ago, correct? Force is also capable of changing shapes.
Yes.
A wall is more rigid, like you said, yes. So it cannot change its shape, or at least the force I apply with my hand is not strong enough to change its shape. Maybe with a bulldozer, I can apply enough force. But a pillow changes shape. That's where the force is absorbed. Got it? Yeah. Okay. Fine. Any doubt in this? Every action has an equal and opposite reaction. If you remember, your collision ka equations are derived from Newton's third law.
What are the equations of collision?
Your collision equation. When you have two bodies, let's say you have body A.
Oh, the collision, the conservation of
Right.
momentum.
Exactly, conservation of momentum of mass m1 or body B of mass m2. Let's
Yes.
say body A is moving towards the right and it collides with body B. Let's say, in fact, that there is a collision that occurs. So due to this collision, body A continues to have the same mass m1, but its velocity has changed. Let's say the initial velocity was u1. It's now changed to v1. Body B, the body with which it collided, now has mass m2 but a velocity v2. Now, think of it this way. Whenever body A collided with body B, body A, let's say, applied a force FAB. So due to Newton's third law, what will happen? When body A applies a force on body B, what will happen from Newton's third law?
There's going to be an equal reaction force.
From which body?
B to A.
So FBA, I'll call it.
Yeah.
So what can I write the equation as? FAB will be equal to
FBA.
will be equal to
FBA.
will be equal to FBA or will be equal to negative of FBA.
Negative of FBA.
Why am I writing the negative sign here? You need to teach
Because it's in the opposite direction.
So you're telling me that the two forces are in opposite direction. So I'm denoting that by negative sign.
Yes.
Why is the negative sign important? Because they're in opposite direction.
Because that force has been
Force is a vector. That's why, correct? I need to care about the direction too, not just the magnitude, right?
Yeah.
Yeah, correct. Force is a vector, so I need to care about direction as well, which I am here. Good. So we also just discussed a page back that force is also change in momentum, correct? mv minus mu by t.
Yeah.
So force applied by body A is nothing but change in momentum by A, which is nothing but m1 v1 minus m1 u1. Is this correct? By t. I'm assuming that force applied by body A is rate of change of momentum for body A. Am I correct?
Yeah.
This will be equal to negative of change in momentum for body B, which is m2 v2 minus m2 u2 divided by the same change in time t, because it's the same collision. Am I wrong or am I correct?
Correct.
So you strike out time because it's the same and you rewrite the equation, you get your collision ka equations. What is the collision equation? m1 u1 plus m2 u2 would have been equal to m1 v1 plus m2 v2. Basically, conservation of momentum says that the total momentum before a collision between two bodies is equivalent to the total momentum after a collision. How do I know this? Because of Newton's third law. Got it? It's the same equation rewritten here.
Yes. Okay.
Simple?
Yeah.
That's all it is. Collision ka equations are not something derived out of thin air. They're just an application of Newton's third law to a collision between two bodies.
Okay.
That's it. This works only if there are no external forces involved, like friction or anything else. Okay?
Okay.
If external forces are involved, there will be a loss of momentum, which means the conservation of momentum will not occur. Okay?
Yeah.
There are two types of collision, no? Can you explain what they are?
Two types of collision. Can you give a hint?
Elastic and
I haven't studied it.
there are two types of collision, elastic and inelastic.
Okay.
Elastic collisions are where, along with momentum, kinetic energy of the bodies is also conserved. That means total kinetic energy before collision will be equal to total kinetic energy after collision.
Okay.
But for inelastic collisions, only the momentum is conserved, kinetic energy is not conserved. Some energy is lost during the collision. Got it?
Okay.
That's the only difference between both of them.
Okay.
Any doubt on this? The collision equations, how they're derived?
No.
No. I'll clear this.
Yes.
Okay. There are different type of forces you need to remember. I'm going to talk about all of them. I'll talk about the standard ones first, like friction. Okay.
Yeah.
What is friction? Can you explain in simple words? There's a
A resistive force
friction is
which
a resistive
acts
force.
which
What
acts
direction?
when two bodies are in contact with each other and are
Okay,
moving
fine.
in opposite directions.
In opposite directions. Okay.
Which
Is there a
basically one
standard direction in which friction acts always?
opposite to the motion of the body.
Exactly. Opposite to the direction of motion of the body always?
Yes.
That is correct. Yes. It is always opposite to the direction of motion of the body. That is right. There are two types of friction, static and dynamic.
Two types of friction. Okay.
Correct. You need to know these because you have come across examples in real world about this. About this. So I'll give you an example. Have you ever sat on the slope of a concrete slab or a hill or grass?
Yes.
Correct. So when you sit, there is always a chance of you slipping away, correct?
Yeah.
So that means if there is a chance of you slipping away or sliding, then there is friction acting on you even when you are in a state of rest, correct?
Hmm.
So that friction is called static friction.
How do we define it?
Static friction is just a friction acting on a body which is on the verge of motion. Or if this friction does not act on the body will move. That is static friction. If you notice, I specifically said slow because if you're on a level ground, there is no static friction. If you're sitting on a level ground, there is no static friction acting on you on the ground because you're not going to move. Correct?
Yeah.
Yeah. So that is dynamic friction. The friction that acts when the body is moving is called dynamic friction. Dynamic friction can act in both cases, when you're on a level ground or on a slope. But static friction is the friction that acts when a body is in rest or at rest. Dynamic friction is the friction that occurs or exists or persists when a body is in motion. Simple example, the act of you walking. When you walk on the ground, you use friction to propel yourself forward, correct? From
Yes.
the ground. That is why when you buy your new shoes get worn out after a certain duration.
Yeah.
The reason they get worn out is simply due to the friction. Got
Okay.
it? Clear?
Yeah.
Yeah. Any doubt in this?
No.
No. This is static and dynamic friction. Static friction is what persists when a body is at rest. Dynamic is when the body is being pulled. Okay?
Hmm.
By logic, static friction will always be greater than dynamic.
Okay.
Okay? I'll give you a very simple way to
Are
understand
you
this.
sure?
If you've ever tried to push a heavy object, do you notice how it's very difficult for you to get the body to move? But once you get the body to move, it is easier for you to keep pulling the body or pushing the body. Have you noticed that?
Yes.
Yeah, that is actually what static and dynamic friction are. When a body is at rest, there is static friction, which is very strong. So it takes a lot more effort for you to get the body to move. But once you get the body to move already, then the dynamic friction is much more lesser than static, which means you will require a lot less effort to keep the body in motion. Got it?
Yeah.
Yeah. Any doubt in this?
No.
No. Next. Stopping distance. This is the distance covered by a body when it is under the effect of friction or any other resistive force. Whenever a body is under the effect of a resistive force, there is always deceleration of a body, correct?
Mhm.
Usually, if let's take an example. Let's take this is a body. This is a body on a frictionless surface. When a body is on a frictionless surface and the only force acting on this is the applied force F, the applied force, the resultant force sigma F will become equal to the applied force, correct?
Can you repeat?
When the body is on a frictionless surface and there is a force F that is applied to move the
Yes.
body, I was telling you that whenever the body is on a frictionless surface and there is a force F that is applied to move the body, I was trying to tell you that the force F will cause positive acceleration.
Okay.
Am I correct?
Yeah.
Because there's only one force moving the body.
Yes.
And more often than not, when there is a friction surface or when there is a rough surface and there is also friction acting on the body, the resultant force equation will now change. The resultant force equation will no longer be just F, it will be F minus the friction, correct?
Yes.
And if frictional force is greater than the applied force F, the body will go into negative acceleration or deceleration. Am I correct?
Yes.
And when acceleration is negative, the
How
body
can
will.
how can the body decelerate when it's at rest?
I was talking about a moving body,
Oh,
not
okay. It's moving
a
body.
body. This was a moving body,
Okay.
a body in motion. Okay, for a
Yeah.
body in motion. And whenever there is deceleration, the final velocity will always come to zero, which
Okay.
means the body will eventually come to a halt.
Yeah.
The distance that it travels before coming to a halt is called stopping distance. That's it. You use the same equations of motion to find stopping distance. There is nothing special about it. Okay. But imagine you're driving a car
Yes.
and let's say that you see something blocking the road. So when you see something blocking the road, you suddenly apply the brakes, right? So that your car stops moving and you don't collide with the object, whatever is blocking the road. So the time that you take before applying the brakes is your reaction time. And after you apply the brakes and when you decelerate your body, the distance traveled before it completely comes to a halt is the braking distance.
Yeah.
You want me to show the same using a graph?
Okay.
I'll show using a speed time graph or a velocity versus time graph. Let's say the body could either be traveling with constant velocity or increasing velocity initially. So this is the part where you have the reaction time occurring, where you're thinking about applying the brakes. But as soon as you apply the brakes, the velocity will ideally reduce uniformly and bring the body to a state of rest. This is the distance traveled in this part or the area in this part. This is your braking distance. Got it?
Okay.
Any doubt in this?
No.
Yeah. Copied?
Yeah, yeah.
Okay, fine. There are other forces that act on a body that we need to talk about. One of them is also weight. We call weight by different names. We call weight as a gravitational force or the force of gravity. Whenever we denote the direction of weight on a body, we always assume it is on planet Earth. Okay. And whenever you are on planet Earth, remember this is the surface of the Earth, your weight or your gravitational force towards Earth will always be acting downwards. This
Yeah.
never changes.
Okay.
Okay. And what is the formula for weight? It is very similar to the formula F equals ma.
Weight equals mass into
W equals m into g.
G.
What is g here? You need to define.
Gravity.
G is not gravity. G is either
G
called
is the
acceleration,
acceleration of free fall. Yeah.
acceleration of free fall or acceleration due to gravity, also known as gravitational field strength.
Okay.
On the surface of the Earth, it's a constant. It's usually taken as 9.81 or approximated to 10 meter per second square. Okay. You can even sometimes take it as 10 as per requirement for numerical. Okay.
Yes.
Any doubt on this?
No.
No. So if you have two bodies, one of mass 5 kg, one of mass 10 kg, which one will experience a greater force or weight? Which one will have a greater weight?
The 10 kg body.
Which one will experience a greater acceleration due to gravity?
The 10 kg body. No, the 5 kg body.
It's a trick question. Both of them will experience the
Isn't it
same
going to be
acceleration.
constant? Yeah, it'll be
Both of them
same.
will experience the same acceleration due to gravity. Got it? So the acceleration experienced by both of them or the gravitational field strength experienced by both of them is the same. That is independent of mass. But the weight experienced and exerted by them is different. That's because the 10 kg mass is much heavier than the 5 kg mass. It will exert and experience a greater weight. Got it?
Yes.
Yeah. Weight direction always downwards because you assume with respect to surface of Earth. Clear?
Yeah.
Yeah. Next, we talk about action-reaction pairs from Newton's third law. Any doubt in that?
No.
A rocket, for example, works on the action-reaction pair. A rocket, as it burns fuel, the gases are exhausted at very high speeds, right? The exhaust gases in a rocket are given out at very high speeds. Is that correct? In a rocket, have you seen?
Yes.
So what happens is, as let's say the exhaust gases are exiting the rocket with a certain value of momentum, mv, m1 v1. Okay, the rocket is moving up with another momentum, m2 v2. Now, before the rocket taking off, the total momentum was 0, correct?
Yes.
So afterwards as well, the total momentum must be equal to, according to conservation of momentum, if the total momentum before collision is 0, after collision as well, the total momentum must be equal to.
But is that possible?
No, I'm asking you, the total momentum
Zero,
must be
zero,
equal to
zero.
0, correct? That is possible because the two bodies are traveling in opposite directions. Their momentum will cancel each other.
Okay.
Total momentum becoming 0 doesn't mean the rocket is at rest. The rocket is moving upwards. The gases are exhausted downwards. But because momentum is a vector, the momentum with which the rocket moves up will be the same momentum with which the gases are liberated downwards, which is why they will cancel each other out.
Yeah.
That's how a rocket is propelled upwards, because the propulsion of rocket upwards is due to the exhaust gases being liberated downward. Got it?
Yes.
Yeah. In a way, the exhausting gases are pushing the rocket upwards. That's what I'm trying to tell you.
Okay.
The exhaustion of the gases at very high speeds is the action. The rocket being propelled upwards is the reaction. A slightly more complex example. The more simpler example would have been you sitting on a chair and experiencing back pain.
Okay.
That's because of the normal force or the reaction force applied by the chair on your body. Got it?
Yes.
Any doubt on this?
No.
Anything you want me to explain again? Didn't understand?
No.
No. Okay. Next, scalars and vectors we've done.
Yeah.
Do I need to explain the addition of vectors using
No.
no? Okay. So just for quick measure, when you try to add two vectors, use the parallelogram law. Complete the parallelogram. When you have two vectors, complete the other two sides. You know the logic of a parallelogram. Opposite pairs of sides are equal and parallel. And when you complete the parallelogram, the diagonal that you draw from one end to the other basically predicts or denotes the resultant of the two vectors.
Yeah.
Got it? This is how vectors are added. Adding vectors is slightly more nuanced than adding scalars because there is direction involved. If the two vectors were in the same direction, you could directly add them through normal rules of addition. If they were in exact opposite directions, you can directly subtract them. But when they are at an angle with respect to each other, as shown in the diagram, you need to use the parallelogram law, also sometimes known as a triangle law, to figure out the resultant of these vectors. This is mostly used in your scale diagrams.
Mhm.
Remember, there is
Yes.
a stream of water flowing at
Yeah.
a speed of 3 meter per second. A person wants to cross it by going straight at 4 meter per second. Find the resultant speed of the person. All
Yes.
those questions. Clear?
Yeah.
Yeah. Next you have centripetal force. Centripetal force is a unique force. This is a force that acts on a body in circular motion. So what is unique about circular motion? I want you to teach. I'll give you the premise for circular motion. You teach me what is unique about it. Okay. Let's take an example of a body in circular motion.
Mhm.
What is unique about it?
That the force will always be applied at right angles to the center.
Force will always be applied at right angles to the center. Teach me. I'll draw a circle here.
Okay.
So here's a
And
circle.
yes.
Let's take the example. Let's draw a body. Let's take the body somewhere here along this circle in circular motion. Let's say that it's going like this anti-clockwise. So this is the direction in which the body is traveling.
Yes.
As opposed to here, the body is traveling in this direction. As opposed to here, the body is traveling in this direction.
Yes.
So if I assume the body is traveling along this circular path with uniform speed, can I also assume that it is traveling with uniform velocity? If I
Yes.
assume speed to
No,
be
no,
the
it
same,
cannot, we cannot because it's constantly changing direction.
correct. So even if I assume the body to be in uniform circular motion, that is the speed to be the same at every position as shown above or here, the velocity is not going to be the same. Maybe the velocity will be the same in terms of magnitude, but not in terms of direction, correct? So
Yes.
you're telling me that uniform circular motion is uniform speed, but variable velocity. Is that
Yes.
correct? So if velocity is changing, should there or should there not be acceleration?
There should be.
And at every point, the acceleration is always directed where?
To the center.
Which means the force acting on the body is also directed towards the,
Center.
because force is always in the direction of acceleration. F equals ma. Correct? So the body's acceleration is towards the center. The body's force is also towards the center. You give a special name to this acceleration and this force. You call the acceleration as the centripetal acceleration. And what do you call the force as?
Centripetal force.
Exactly. Correct. Yes. You call the force as centripetal force. Any doubt in this?
No.
Any doubt you want me to explain again?
No.
No. So you're telling me that centripetal force is that force acting on a body always towards the center. And this force, how is this important, or what is the relevance of this centripetal force?
It allows an object to move in a circle.
So you're telling me that if there is no centripetal force, the body will not continue to stay in circular motion?
No, because there will be nothing keeping it in that, because there'll be no force holding the body while it's
Then
moving.
what is centrifugal force? Because I've heard this word also, centrifugal. I don't know what that is.
Okay. I think
What's centrifugal?
centrifugal force is the opposite of centripetal force and
It's a
pushes.
force acting away from the center, correct?
Yes, and pushes the body outward, but it's still in a circular motion.
Is it which one of these two are imaginary? Which one is real between centripetal and centrifugal?
I think centrifugal is real.
Ulta.
Oh,
Centrifugal is imaginary.
okay.
I know it seems that way because I remember this too. I imagine myself going on a merry-go-round on an amusement park ride, let's say. Have you gone on a merry-go-round or any
Yeah,
other
yeah, yeah.
ride that goes in a circle?
Yeah.
So you might have experienced this or in a playground also. So if you've done this, you'll notice that you'll always feel like you're being pushed away from the center. And you need to apply a force to keep yourselves toward the center, right? Whether it is holding on to a rope or pushing yourself inward, trying to apply friction between the surface and your shoes. So you do all these to pull yourself towards the center, correct?
Yes.
So to you, the person in circular motion, it feels like the force that is pushing you away is real. You applying a force is imaginary, but it's the opposite. The force that you feel which is pushing you away, that is centrifugal force, which is the imaginary force. The force that you apply to keep yourself or to pull yourself towards the center, whether it is tension in a rope or friction between your shoes and the ground to keep yourself in circular motion, that is centripetal force, which is real. Got it?
Okay.
Clear?
Yeah.
Simple examples of centripetal force can be this. If you take a stone, tie a thread to the stone, and if you rotate it horizontally, you'll notice that there is tension between the stone on the thread, correct? Acting towards the center. This tension is what acts as the centripetal force, keeping the body in circular motion. Clear?
Yeah.
A more real-time example, you know that the moon revolves around the earth, correct?
Yes. The
Why
first.
does correct? The moon and the earth experience gravitational force of attraction towards each other. Obviously, both experience the same magnitude of force. The gravitational force, which keeps the moon in orbit around the earth by acting towards the center of the earth, this is what acts as a centripetal force, keeping the moon in circular motion around earth and keeping the earth in more or less circular motion around the sun. Got it?
Yes.
The orbit isn't exactly circular, it's elliptical because there are more complex forces, conditions involved. But as far as you're concerned, you can assume it to be circular. We do too when we are understanding the concept of gravitation. Okay?
Yeah.
Yeah. Any doubt in what is circular motion and what is the importance of centripetal force, centrifugal force?
No.
Just one sentence again at the end as a summary. Centripetal force is real, centrifugal is imaginary.
Yeah.
If you ask me to show what is centripetal force, I can't show you. Like how I show what is weight, what is friction, what is normal, I can't show you what is centripetal. All these forces, weight, gravitational force, friction, tension, all normal, all of these forces act as the centripetal force during various examples of bodies in circular motion, and they help keep the body in circular motion by acting towards the center as the centripetal force. Got it?
Yeah.
Any doubt on this?
No.
No. Clear?
Yes.
Here's an example of a person doing the same thing that I said. He or she is has tied a stone or a ball to a thread, and when they rotate it horizontally, the tension in the thread acts as a string acts as centripetal force. And when the string breaks, the body will be thrown off tangentially along its direction of motion or direction of velocity. Got it?
Yeah.
Yeah. Any doubt in this?
Forces at velocity.
So I'm sorry.
Nothing. Just reading.
Okay. Oh, you want me to go
No,
back?
no.
This one only, no?
Skim through it. Yeah. Done.
Okay. So here's an example of a linear force and a centripetal force. Centripetal force always towards center, linear force along the direction of motion.
Okay.
Okay, linear force is also called a translational force. This is centripetal force. Again, centripetal force is what keeps satellites in orbits around Earth and Earth or other planets in orbit around the sun. Okay.
Yes.
And on a micro level, coming back from macro, it is what keeps electrons around the nucleus as well, along with other forces, which you will learn in higher grades. Okay.
Yes.
Okay. Fine. Let's learn about the turning effect of a force. If you remember when I spoke about different effects that force can have on a body, I told one of the effects is also the turning effect, correct?
Yes.
So the turning effect of a force is given a special name. It's called a moment. As far as you're concerned, a moment has only two possible directions. It can either be clockwise or it can be anti-clockwise. So formula for a moment, very simple. Moment of a force is nothing but the
Force.
product of force into, yes, tell me.
Force into perpendicular distance from the point.
Exactly. And what is the condition for equilibrium in such a state or such
That the
moments?
total moment, the sum of anti-clockwise and clockwise moment has to be 0.
Correct. There are two ways you can interpret it. Some books say the sum total of all the moments must be equal to 0.
Or
When they say that,
the
they mean that assume clockwise as positive, anti-clockwise as negative, so on and so forth. Or another way to interpret is sum of all the moments acting clockwise on a body,
equal sum of all the movements acting anti-clockwise to the body.
and this means the body is in equilibrium. If there is an imbalance, then the body will be in equilibrium. Got it? You use this equilibrium condition to figure out the missing force or the unknown values of forces or distances for a body in rotational equilibrium. Am I correct?
Yeah.
Any doubt in this?
No.
You figure out whether the moment is clockwise or anti-clockwise by looking at the position of the pivot or the axis of rotation. Correct?
Yeah.
Yeah. So this is called the principle of moments. Can you give me an example? Can you tell me which all moments are clockwise and anti-clockwise here? For example, here, this is the pivot. The force seems to be acting downwards. So is this contributing to a clockwise moment or an anti-clockwise moment?
Clockwise moment.
Good. What about this? The same
Anti-clockwise.
pivot. Same one.
Anti-clockwise.
But this is acting at an angle. So what do you do in that case?
So you use the formula of cos theta.
Correct. So you can do one of two things in this case. Here, I've taken the perpendicular distance in this direction, which then you can just multiply, or if you want, the same example, you can solve it another way. The same example, because the force is acting at an angle like this, find the components of the force. For example, if this angle is theta, then the cos theta component. Like if this is force, it's cos theta component. F cos theta will be the perpendicular force. Take that force and then this perpendicular distance, figure out the moment. Got it?
Yes.
Or find out this direction or this distance. Both the ways you can do it anyways. If it is perpendicular, then no problem. You can directly multiply force into distance. If it is at an angle, either find the component of force or find the shortest distance between the pivot and the force and multiply that distance. Got it?
Okay.
Do one of those two. Don't do both. Am I clear?
Okay.
And this, again, you can use principle of moments to figure out missing forces or distances when conditions of equilibrium are explored. Any doubt in this? Anything you want me to explain again? Didn't understand?
No. Just one question.
Sure.
Whenever force is acting at an angle, so we first draw the force perpendicular to the line of action of force.
No,
And
you don't draw it perpendicular. It's usually the direction is already stated before, and almost always, yes, it is perpendicular.
okay.
Yeah. What was your doubt?
That's it. That's it.
That was a doubt.
Yeah, just like how to calculate, how to get the angle.
Perpendicular force into perpendicular distance. That's it.
Yeah.
Always.
Yeah.
Even when it is at an angle, take the shortest perpendicular distance or take the component of force in that direction to get the perpendicular force. And then multiply the actual distance. Got it?
Yes.
Yeah. No matter how you do, you should get the same moment. Clear?
Yeah.
Okay. Next. Here's an example of the principle of moments being used to figure out whether the body is, in fact, in equilibrium or not. Here you can take the pivot about two positions. You can take it about the center O, or you can take it about the point P. What is the advantage about taking it about the middle point O?
We know that it will be balanced at point O because it's the center.
You don't know. You only know after you do the principle of moments and to figure out whether clockwise equals anti-clockwise. Correct? That's the whole point.
We can measure it. It will be easier to measure the distance then.
From the center?
Yeah.
No, I don't think I can accept that argument. It's just measuring, no? How will it matter whether you measure from an end or in the middle? The advantage is you don't have to worry about the weight of the scale, which is acting downwards at the center.
Okay.
Correct? Because the weight will be acting exactly at the point of pivot.
Okay.
And if a force is acting or if the weight is acting exactly where the pivot is, then it is not contributing to any moment at this pivot, at O. Correct?
Yeah.
So I can ignore the weight of the scale if I take the moment about O. If I take the moment about point P, then I have to take weight into account. Weight will contribute to what type of moment? Clockwise or anti-clockwise?
Clockwise.
Correct. So if you take the moment about point P, if you notice all the forces seem to be acting downwards only, including the weight. So there is definitely obviously an inequilibrium condition, which means all the moments are acting clockwise and then anti-clockwise. But if there is a reaction force acting upwards, then in that case, yes. Then the body could be in equilibrium about point P as well. Got it?
Yes.
Yeah. So remember, there is no hard and fast rule that you have to take the moment about the center or about any particular point. You can take it about the center or any other point as well. Remember, wherever you take the pivot, the force acting at the pivot is always ignored because it doesn't contribute to any moment about that pivot. Got it?
Yes.
Like when you take in the center, you always ignore the weight of the scale, which acts at the center. Got it? Or you assume that the scale is weightless. That's another way you circumvent the problem. Okay? Any doubts in this?
No.
Sure?
Yes.
Okay, fine. In fact, in this example, you can take the moment about point P to figure out this reaction force acting in the middle as well. Okay?
Yeah.
Yeah. Next. You also have the concept of center of mass. What is center of mass? Can you define? We come across this concept a lot.
Yeah, it's the point on an object where the entire weight seems to be concentrated.
It's the point about the object about which the entire mass seems to be concentrated. Okay, I agree. That is correct. Or can I say it is a point on the body about which all the forces are assumed to be acting?
Yes.
Yeah. Center of mass for symmetrical bodies is very easy to find out. It's exactly at the center.
Yes.
For bodies which are not symmetrical, the center of mass, remember, is more inclined towards the part of the body where more mass is concentrated. Correct. That's your general rule of thumb. Figure out where center of mass is. And what does a lower center of mass signify?
Stability, higher stability.
Correct. A higher center of mass means more less stability. That's why if you've ever wondered about the science of building construction, buildings are always constructed such that the entire building has a lower center of mass so that it's more stable and less susceptible to to being toppled. Oh, okay.
Yes.
Next, you also inquire about the different types of equilibrium.
Yes.
The different types of equilibrium are a stable equilibrium, an unstable equilibrium, and a neutral equilibrium. All these types of equilibrium, you can notice they are only dependent on the center of mass. A lower center of mass and a body at rest indicates stable equilibrium. A higher of center of mass while at rest indicates unstable equilibrium, which means the equilibrium can be disturbed much more easily. That's what unstable equilibrium means. Neutral equilibrium is somewhere between unstable and stable.
Okay.
Got it?
Yeah.
Yeah. Any doubt in this?
No.
No. Here are some examples. You can look at both the examples here, I guess. This is the example question, and then here's the solution for the same. You can try this question if you want. I'll give you 2 minutes, and then I can show you the solution.
Okay.
Yeah.
Diagram on the right shows a model crane. The crane has a counterbalance weighing.
I think the diagram is missing, no?
Yeah, which is
It's on the next. It's on the next this thing.
Yeah.
I'll show it to you. Read the question. I'll show you the diagram.
0 to cope with different loads. With no load, the top section would balance. How far O should be placed? Okay.
I'll show you.
Yes.
Here's the diagram.
Okay. So the first part was how far O should be placed.
Correct.
Okay.
So to figure this out, you can take the moment where, about which point.
About O. The
But you don't know where O is, right?
wait,
Because
just a second. With the okay, how far? Yeah.
you,
So
you don't know O or you know O from the
how
diagram. You do
far
know
from
where O
O?
is, correct? Yeah. Okay. So you can take the moment about O and you can place it. Okay. I have one other question though. Okay. I think this distance is what they're asking, correct?
Which distance?
This.
No,
Correct?
I think they're asking the other distance.
Are you sure? Because the other
How
one is already at
far?
the edge.
How far from O should the 100 Newton load be placed? Could you go back to the question?
Is it? Okay, let me
Yes,
check.
sir.
Let me erase this part. Oh yeah. With the 100 Newton load
Oh, okay,
shown, how
shown.
far should
Okay,
the
yeah.
other one? Other
Counterbalance.
one only, I think.
Yeah,
Correct.
the other one.
So just use principle of moments, you'll get the answer. You know the
So,
answer has to be between 0 and 1 meter.
yes.
Yeah.
So we'll do 100 into 2 upon 400.
Is equal to 400 into x. You can say yeah, upon 400. Answer?
Yeah. 100 into 2 upon 400. 1 by 2. 0.5.
That's clear.
Yeah.
Yeah. Part 2 again. You can solve the exact same. What is the maximum load can safely lift? To find the maximum load, you
Yeah.
can yeah, what can you do to find the maximum load it can lift?
I don't know.
Simple. Look here. The load is here on this side, correct?
Hmm.
So you know that the moment acting on the right hand side, that is a moment clockwise, is fixed, correct?
Mhm.
The moment anti-clockwise is also fixed. Yes, so that the equilibrium is maintained. But even though momentum is fixed, force and distance can be manipulated. They say what is the maximum load that can be used. That means to maximize the load or the force
The
applied,
distance
the
is to be
distance must be reduced. Correct. Take the minimum or the least possible distance. You'll get to know the maximum load that can be placed.
0.1 meter.
Yeah, you can take that. And then you'll get the, assuming the same moment, you'll get the maximum load that can be placed to achieve this, to pick the highest. Got it? Any doubt?
So, just a second.
I'm sorry.
Just a second.
If you assume 0.1 meter, okay,
It's going
fine.
to be 2000 Newton.
2000 Newton. That is fine. Correct.
Okay.
They've assumed the minimum distance to be 1 meter.
Hmm.
And then using, sorry, the minimum distance to be this much. And the maximum F is 200. So the load is 400 Newton.
Hmm.
Clear? Because 200 into 2, 400. That's the maximum value.
Okay.
Clear?
Was my answer right?
Yeah, your answer is right. Assuming that because I give you the condition that the moment on the right hand side is fixed. I didn't change that. So
Oh,
assuming that and the least distance to be 0.1 meter, yes, your answer is correct.
okay.
But here they're making the assumption that the 400 Newton value ka counterbalance can be shifted to the end, making the total moment on the right hand side, the clockwise moment, to be 400 Newton meter. So the moment on the left hand side also can be 400 Newton meter, which means the highest, assuming the distance is 2 meters, the highest value of load that can be applied is 200 Newton, according to them. Here, do you see?
Hmm.
Yeah. Again, it depends on the conditions given. I change the conditions from what they have given. Okay.
Okay.
I let you vary the distance also, which they have not. They've kept the distance as 2 meters. The last concept is stretching and compressing. I'll discuss this and then I'll give you a small break. Okay. Whenever I stretch a body, if I draw a graph of extension versus load, you always notice this peculiar behavior. You notice two peculiar points. One is a point up until which the relationship seems to be linear or a straight line. And the second point is a point beyond which the relationship is non-linear. Do you notice this?
Yes.
Do you know what the name was given to this point and this point?
The limit of proportionality is x.
Correct. This is the limit of proportionality. What is limit of proportionality?
The point till which the spring or the elastic material can get stretched without getting deformed.
What is this?
The extension? No.
Elastic limit.
Okay.
The limit beyond which the body will not regain its original shape.
Okay.
Got it? For example,
How are they
here,
different?
they're different because limit of proportionality is the limit before which the load versus extension is a linear relationship. After limit of proportionality, the relationship is non-linear, but still, if you remove the load or the force applied, the body should regain back its original shape. But beyond the elastic limit, it will not regain the original shape. It will have some permanent deformation. That is called the elastic limit. Got it?
Yes.
Just remember this. Limit of proportionality means the point up until where relationship is linear, or F equal to Kx. Your formula is there, no? That is obeyed. Elastic limit is that point up until which the body will regain back its original shape once force is removed. Beyond elastic limit, it won't regain the shape. If you notice the dotted line, when I remove the force applied, it will have some permanent deformation or extension. Got it?
Yeah.
That is the elastic limit. Clear?
Yes.
Any doubt in this? What is F equal to Kx? K is called the spring constant. K is force per unit extension, or F by X, measured in Newton per meter.
Okay.
Any doubt in this?
No.
A greater spring constant means the body is able to, what? For the same force, the body will expand much lesser. Got it? Yeah. Any doubt in this?
No.
No. This is one of the other effects of force. Force can also change the shape of a body, as explored here. Got it?
Yes.
Extension is always new length minus original length. Don't forget to make that assumption.
Okay.
Here, extension is the change in length. It is neither the new length nor is it the original length. It is the change in length which is measured by subtracting new length minus original length, or original minus new in case the spring is compressed instead of being expanded. Okay? Yeah. Any doubt in this? No. So this is the definition of limit of proportionality and the elastic limit. They're different. They're not the same.
Yeah.
Students always have this confusion. They assume the limit of proportionality and the elastic limit are the same, which is not the case. Got it?
Okay.
Yeah. Any doubt in this?
No.
No. The formula F equal to Kx, I just did not name it. It's called the Hooke's law. Okay. Any doubt in this?
No.
No. Okay. The last concept you have is pressure. Pressure has two formulae by definition. One for a solid, one for a liquid. Pressure due to a solid is pressure P is force per unit area. Pressure due to a liquid, you remember the formula?
Yeah. It's
What is it? Correct. H rho g or rho g h. Pressure is a scalar or a vector?
Pressure is a vector.
Scalar.
Why? It's applied in a direction.
No, it is applied in all directions, which means it is independent of directions.
Oh,
That's
okay.
the whole premise.
Okay.
Got it?
Yeah.
It is applied in all directions, which means it is independent of any, or it doesn't care about which direction it is, because it acts in all directions. Clear?
Yeah.
Yeah. That's it. Pressure in liquids, rho g h formula. Hydraulic systems use the concept of pressure to lift heavy objects. How do they work? Simple. A hydraulic jack looks like this. Look at the diagram on the left and compare it to the diagram on the right. The diagram on the left has a force of just 12 Newton being applied. And this 12 Newton force is able to be converted into 120 Newton force. How does this work? I told you pressure is a scalar, which means it acts in all directions. Is that correct?
Yes.
Do you notice the pressure of this liquid being applied in all directions?
Yes.
And do you notice that here the surface area A1 is much lesser than the surface area A2 here?
Yes.
But the pressure applied is the same, correct?
Yes.
So you're telling me, I'm telling you, pressure P1 will be equal to pressure P2, which
Yeah.
means force F1 by area A1 will be equal to force F2 by area A2. Rewriting this formula, force F2 by F1
Mm.
will be equal to A2 by A1.
Yeah.
So if I increase area A2 when compared to A1, I can increase force applied F2. So just by applying a force of 12 Newton, I can lift an object as heavy as 120 Newton. Just by multiplying the area by a factor of 10. I'm multiplying force also by a factor of 10. Do you notice?
Yes.
All of this is occurring because pressure is a scalar, or pressure applied at this point is same as pressure applied at this point because it is a scalar. Got it?
Yeah.
Okay. Any doubt in this?
But isn't the area greater, so more pressure is being? Oh, the force is the same. Pressure is different. Okay.
Force is more.
Yeah.
Pressure is
Pressure
same.
is different, right?
Pressure is same. That's what I'm
How
trying
can
to
it
tell
be
you.
same?
Because pressure does not care about direction,
But it
nor
cares
the sur-
about the area.
it cares about the area. Correct. That is why a greater force is applied, so that pressure remains the same. If you notice, here the pressure is 12 Newton divided by 0.01 meter square, correct?
Yes.
And here on the right hand side, the pressure is 120 divided by 0.1 meter square. Both of them are the same, aren't they? A greater surface area means a greater force applied, but the pressure remains the same.
So force is changing.
Correct. Pressure is force per unit area. Think of it this way. A packet of Maggie costs 12 rupees, correct?
Yeah.
It's 12 rupees whether you order it on Blinkit or go to a physical store and buy it. Yes?
Yes.
But the total price will change whether you buy 3 packets or 5 packets. Yes?
Yes.
But because the total price changes, can I say the price per packet of Maggie is also different?
No.
So the price per packet, imagine that to be the pressure.
Okay.
The total price is the force. Think of it that way.
Okay.
So the pressure is the force per unit area. The force applied per unit area remains the same in both the cases. The total force is different because the total area is different. But the force applied per unit area, which is the pressure, is the same in a hydraulic lift.
Okay.
Got it?
Yes.
But I don't understand one thing. This seems to be in violation of law of conservation of energy, won't it? How can I apply 12 Newton and get 120 Newton? How does that work? That seems like a scam, doesn't it?
Because the area has been increased.
But still, that doesn't explain how 12 Newton can be converted into 120 Newton magically like that. So what's happening here? Where is how will you explain this using law of conservation of energy?
Does the oil which is there in the pipe tube
Nothing
will
happens to the oil. Nothing
Okay.
happens to the oil.
Okay. So
Think. I'll give you a 10-minute break. Think on this. The clue is in the concept of work done. Okay.
okay.
I'll use work done to explain this. You also think about this. I'll give you a 10-15 minute break. I'll start exactly at 7:30 again. Okay.
Okay.
I just need to do work energy power efficiency. I'll do that.
Okay.
Fine. Think about this. You can take a screenshot if you want.
Okay. Yeah, I will.
So the concept of work done is supposed to be used to explain how law of conservation of energy is not violated in this exam. Okay.
Okay.
Do this. Pressure from a gas, I will do when I do chapter 2. Okay.
Okay.
Yeah. Now I'll just give you a break and then I'll talk about work energy, power, and efficiency for the remainder of the class.
Okay.
In the previous example, All these Boyle's law, gases and all, I'll do in the next chapter. Okay. Pressure has both parts. Pressure has some parts in the first chapter and some in the second. I'll do it in the second part. Anyway, I was talking about this hydraulic lift.
Yeah,
Where do you
so
think this thing?
I used the chart section when I was solving. I just
Correct.
sent
You
an
said
answer
work
again.
done equals force into displacement.
Yeah, I was just trying to like whatever was coming down, just pen down there
Correct,
and
correct,
then
correct.
waited for you to come back. So just because there's a distance between the place where the force is being applied and where we have the output, so
Yeah.
that distance is going to increase the energy.
Actually energy won't increase. That was my problem,
No,
right?
not
The energy
the
applied is the
energy,
same.
the output,
The
the force.
distance will reduce. Correct. So if you notice here, let's say I moved this 12 Newton a distance of 10 meters.
Oh, this
Okay.
distance.
Correct. So what was the total work done? Force is 12 Newton, displacement is 10 meters. What is the work done?
120
Joules, correct? So this object, which is 120 Newton, would have moved just 1 meter. Thereby, the total work done here is also
the same.
understood. This is how law of conservation of energy is obeyed here.
Okay.
Got it? So if you notice, energy is neither created nor destroyed, just converted from one form to another. By the way, in reality, it won't even be 120. It will be lesser than 120 because efficiency is never 100%, right?
Yes.
It's always lesser than 100. Clear?
Yeah.
Okay. So the distance that it moves will be less. So applying 12 Newton for 10 meters will cause a 120 Newton body to be lifted through just 1 meter. But as long as you're okay with that offset, you can apply a smaller force to lift a heavier object. That's how, more or less, that's how your gears also work.
Okay.
Okay. Yeah. Any doubt in this?
No.
No. Next, I'll talk about work done in general. What is, how would you define work done?
Work done is the force applied in a particular distance.
In a particular direction.
Yeah, in a
And
particular
the
direction
displacement.
to move
Correct.
a body.
Or to displace a body. Correct. Work is said to be done only when the displacement occurs in the direction of force applied.
Yes.
For example, if force and displacement are perpendicular to each other, then work done is 0.
Yeah.
Correct. What about this? Can work done be negative?
No.
Can work done be negative?
Work done being negative. No.
It can.
Can
Work done
you
is a
push
scalar or a
work?
vector?
Work done is a vector. Oh, it can be negative when you're pushing a wall, maybe.
Think of it this way. Look at this pen. You see this pen? I think I've blurred my background.
Yeah.
You see this pen in my hand?
Yes.
So when I let go of it, there was displacement of the pen, correct?
Yes.
Downwards.
Yes.
And the force applied in that case was the weight, its own weight or gravitational force. But regardless, the gravitational force was not applied by me, correct? So the displaced, so I did not contribute to work done. Gravitational force did, or gravity to be specific. So work done by gravity will be positive. Work done by me in displacing the pen will be negative in that case. Got it?
Yeah.
Work done is negative usually when something else or someone else does the work for you. Another example, work done will be negative when force and displacement are in exact opposite directions. Think of it this way. You're trying to push a tire uphill, but the tire is so heavy that it continues to fall back downward.
But then you said work done is negative when force and displacement are in the opposite direction. Am I right?
Correct. So if
How
you're trying to
does
push a
the
tire uphill, but it is so heavy that it keeps falling back downhill.
but
In
then
that
how
case,
does that pen example work here?
the pen example is just not falling at an angle, it's just falling straight down. That's it.
Yeah,
That's the
and
only difference.
that's where the force is applied, no?
I'm sorry, that's why.
That's where the force is applied, no? The gravitational force
Correct.
is also
Correct.
acting.
That's why I said work done by gravity is positive, work done by you is negative. That's why I said that.
Oh, okay.
Additional sentence. Got it?
Yeah.
Work done is a scalar or a vector?
Vector.
Scalar. Even though it's a product of two
Right?
vectors, it's a scalar. It's a scalar because work done does not depend on the direction in which the body is moved. It only depends on the initial and the final position of the body moved.
But the distance
and
has to be in the like the direction in which the force is applied, no?
correct. But work done, how it is defined as a quantity such that it only depends on initial and final position. I'll give you an interesting example to teach you why work done is a scalar, not a vector. Okay. Let's say that you live in the third floor or fifth floor of a building. Okay. I'll give you a heavy box to lift.
Yes.
And then I'll ask you to take it from fifth floor to ground floor.
Okay.
So physically speaking, you will do work, correct?
Yes.
To carry the object from fifth floor to ground floor.
Yes.
And I'll ask you to bring the same object from ground floor back to fifth floor.
Yes.
At the end of it all, will you be tired or will you not be tired lifting
Yes,
the heavy object?
I will be.
So physically speaking, you did do work, but
Yeah.
according to physics, work done by you is totally zero because your initial position is the fifth floor. Your final position of the object is also the fifth floor. So according to physics, work done will be zero or energy spent will be zero. Even though, yes, practically speaking, you will be tired from carrying the body from fifth to the object, sorry, from fifth to ground and ground back to fifth floor. So there is a difference in how we physically understand work and how it is defined according to physics. Work done is defined to be a scalar because it only depends on the initial and the final position, not the path taken. If it depended on the path taken and if it were a vector, then work done would not be zero in my example. Got it?
Okay.
Clear?
Yes.
There's a difference. If you ask me, if you still ask me why is it a scalar, that is just how I've defined work done. That's it. That's all. I don't have an answer after that.
Okay.
Okay?
Yeah.
Yeah. It's just how I define a quantity. If you want me to be even more naked with the truth, I can just tell you work done is a make-believe concept. Correct?
Okay.
Because it's a make-believe concept, I define the rules. I decide the rules. When I say I mean the rules set forth by physics. Okay?
Yes.
Yeah. The same also applies. If you remember, I told you this long ago also when we were discussing current, voltage, resistance. If you ask me to show where is current, where is voltage, where is resistance, I will draw a blank. I can't show you in a circuit where current, voltage, resistance are because they are make-believe, made-up concepts by me to understand and interpret and exploit or manipulate how a circuit works. That's all they are. Okay. That's all their purpose is. It's to help me understand a phenomenon so I can manipulate it to my advantage. If you notice, that's all physics is, right?
Yeah.
The ultimate goal of understanding anything is to exploit it to your advantage, right?
Yes.
Yeah. That's what we try to do with everything around us. Even the most noble of uh, 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 let's say things we do, whether it is trying to understand how the cosmic array works or how astrophysics or when we dwell in more deeper concept in astrophysics, the end goal is still the same, right? To interpret the world around us so that we can not only understand it better, but also exploit it a lot more or a lot more efficiently, so to speak, right?
Yeah.
Yeah. So this is work done. I think I strayed off the topic, but coming back, this is what work done is.
Yes.
Any doubt in what work done is defined as? What is its formula? Okay, whether it can be positive or negative. Work done is very special because even though it's a scalar, it can be negative. It can be negative under two conditions: when force and displacement are in exact opposite directions, or when something else or someone else is doing the work for you. Then work done by that someone else or something else will be positive. Work done by you on the body will be negative. Okay.
Yes.
Next, what is energy? You've learned this, no? You've been learning this since class 4, 5. It's the capacity to do work, correct?
Yes.
And dynamically or dimensionally speaking, work done and energy are practically the same.
Yeah.
Energy consumed equals work done,
Okay.
or energy stored equals work done. Okay.
Yes.
So energy, you can tell energy is the capacity to do work, or mathematically speaking, for a body, the work done on the body will be equal to the energy consumed. Okay.
Yeah.
Fine. There are different forms of energy. What are all the different forms of energy? These here are some of the common ones you know.
Kinetic
Can you
energy.
some which are not in this picture?
Okay. Okay. Internal energy.
Correct.
Uh, nuclear
Electrical,
energy. Yeah.
nuclear, electrical. What else?
Thermal.
Thermal. Correct. What else? There are many
Um,
more. Wind energy,
mechanical, hydroelectric.
mechanical, hydroelectric is I mean there are different forms of energy that occur. Okay, I can say hydroelectric,
Tidal power, wave power.
tidal, correct, geothermal, all of these, right? Yes. Kinetic energy, you have formulas for kinetic and potential, however.
Yes.
Can you tell me those?
So, kinetic energy is half mv square
Correct. And potential
and
is?
mgh.
Correct. What is energy store and what is energy transfer? Can you teach me that?
So, energy transfer is when energy is changed from one form to another.
Okay. What is
And
energy store?
energy store, when an object has energy in itself, maybe it's
In a
potential
particular
energy
form,
in a
that form
particular,
is
yes.
usually considered as an energy store. Can you give me an example of energy store and transfer in a single energy transaction?
Okay, for example, a battery has chemical energy stored in it, and when it's used, so that maybe in a remote, so that energy is transferred.
Transferred into electrical. You have to tell
Electrical.
that.
Yeah.
Correct. Transferred and consumed directly without being stored as electrical energy. Correct. But stored as chemical. When water falls from a height in a hydroelectric power station, water is stored initially at a height as potential. So it's an
Yeah.
energy store. As it falls down, potential gets converted to, as it
Potential.
falls down, potential gets
Potential.
converted into
Kinetic.
energy transfer. Kinetic is then used to rotate a turbine, which
Elec
is what?
mechanical.
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 And then further
Then
by the
mechanical,
generator.
I was talking about AC generator now.
Yes, generator.
AC generator converts mechanical energy into electrical or
Yes.
force into current. That's it.
Okay.
Okay.
Yeah.
Yeah, that is energy store and energy transfer. Here are other forms that you spoke about: radiation, thermal, nuclear, electrical. So this is energy store, energy transfer. The law of conservation of energy is universally binding. It just says that energy can neither be created nor destroyed, just
Okay.
transferred from one form to another. I explained this using hydraulic lift, right?
Yeah.
You can't generate energy, you can't just convert force from 12 Newton to 120 Newton. There has to be a trade-off that occurs. That trade-off was the displacement of the body. Got it? Yeah.
Yeah.
Energy is also wasted when it is transformed between forms. One simple way to understand energy transformations is using a diagram known as a Sankey diagram. You've learned this.
Yes.
A Sankey diagram is by scale a way to understand energy transfers. For example, here, this length is an indication of the amount of the chemical energy stored in muscles. This is an indication of the energy wasted in body as thermal. This is an indication of energy wasted as thermal and air resistance. And this is other forms of energy, the conversion. A Sankey diagram is a scale diagram which helps us understand the input, energy store, and the energy transfers that occur during any interaction involving energy stores and transfers. The thickness of the arrow will indicate the magnitude of the energy that is dissipated through these forms.
Okay.
Simple?
Yeah.
Okay. This, if you notice, is very thick. That means a lot more energy is wasted as thermal energy. Got it?
Yes.
Followed by, which is the next highest form of energy consumption?
Thermal energy.
Thermal energy in ground.
Yes.
The next highest, I think in no order, seem to be this, and this. The thickness will indicate the magnitude of energy. That's what I'm trying to tell you.
Yeah.
Clear? Any doubt in this?
No. No.
No. Potential and kinetic, you know the formulas.
Yeah.
The last formula you need to know is efficiency and power. As
Yes.
far as you're concerned, the formulas for power and efficiency are very simple, at least in mechanics. What are the formulas for power? Power P is equal to
Energy upon time.
work done by time or energy upon time. There is also a formula in terms of force and velocity. Work done is force into displacement, correct?
Yes.
And displacement by time is velocity. So power can also be written as force into velocity. This formula is applicable assuming force is a constant or a uniform force is applied on a body. Got it?
Okay.
Any doubt?
No.
In electrostatics, however, you've learned 3 more additional formulas. Vi, what else?
Vi, then there was just I square R,
All, also.
and then will V square Y.
What is efficiency?
Efficiency is the ratio between the useful energy, the useful
Useful
energy and the
energy
total
or
energy.
power output divided by total power input or energy output by energy.
Yes.
So colloquially speaking or grammatically speaking, when you say someone is efficient, you could also mean that they take less time, correct? To do a certain task or work. But in physics, efficiency is only measured by your ability to convert input to output. The more
Yeah.
efficient you are in converting all of your input to output, power or energy, the more efficient you are as a system or as a machine. Okay?
Yes.
Any doubt in this? The formulas?
No.
No. Yeah, I can give you a minute to write on the formulas if you want.
No.
If
No.
you've noted them down, then I'm good.
Yeah. It's good to go.
Okay, fine. So this completes your unit 1. I've covered all the topics. Again, these are just examples exploring energy conversions. And again, the different forms in which energy usefulness of energy, the how pollution can cause a problem when discussing energy consumption, all of these. I think we also didn't talk about renewable, non-renewable, correct? What are
Yeah.
renewable and non-renewable sources
So
of
sources
energy?
of energy which can get replenished in a lifetime and are not in and are not finite.
They could be finite, but the fact that they can be replenished within
Yes.
a reasonable amount of time when compared to normal human consumption, yes, those are renewable. For example, hydroelectric, tidal, wind, wave, geothermal are all examples of renewable in that definition. Non-renewable examples include fossil and nuclear energy. Okay. I think other examples of renewable also include solar, biofuel, and biomass. Okay. Exhaustive and exhaustive is what you said, finite, infinite.
Yeah.
Solar energy is inexhaustive, whereas can you give me an example of energy that is exhaustive? Fossil fuels?
Fossil fuels or nuclear energy.
Yeah, also exhaustive. Okay. Any doubt in this?
No.
No. So this completes unit 1. Next class, I'll be going with thermodynamics and temperature and gases.